Today's lesson is lesson 5.1, Attributes of Quadratic Functions from Graphs. Quadratic functions can be written in the form f of x equals ax squared plus bx plus c. Here are some examples and some non-examples of quadratic equations. What I want to draw your attention to is that in the examples, I always have an x squared term, and this is my highest term, while in the last one, the variable changes from x to t. But notice in my non-examples, I do not see that square. I see just x, or I see a number raised to a variable of t, or I see an x to the third power. Once I get a power that is greater than 2, I no longer have a quadratic. And here I just have an x once again. All right. Quadratic functions have a U-shaped graph, which are called parabolas that can open upwards or downwards. We're going to see what that looks like in today's lesson. The domain of my quadratic function is the set of all values, my independent x values over the range over which the function is defined. Remember, these are my x values. The range is the set of all dependent or y values. Let me go ahead and change that. There we go. Of the relation of the function. A quadratic parent function is the function f of x equals x squared. And you can see that right here in this graph. It has a domain of all real numbers. You can write out the word all real numbers like I have, or you can use this symbol for all real numbers. It has a range of y is greater than or equal to 0, which can be written as all real numbers greater than or equal to 0. We can label the function's minimum value and axis of symmetry on the graph. The minimum value, let me grab my pen. The minimum value is right here at 0, 0. And my axis of symmetry would be a vertical line that runs right through my minimum value. It is called the axis of symmetry because, as you can see, the points on both sides are the same distance from that line, 1 and 1. Here I have one that's 1, 2, and so right here I have 1, 2 as well. Remember, when we're counting distance, it doesn't matter that this point is on the negative and it's 1, 2, counting in the negatives, because we're counting distance, they're both the same, 2 and 2. And that's what the axis of symmetry allows you to do. It allows you to graph one side of the parabola and then mirror it to the other side as well. Let's go ahead and take a look at example 1. We're going to go ahead and we're going to circle the equations and the graphs that appear to represent a quadratic function. But remember, as we look here at our equations in the top row, we're looking for an x squared and only an x squared. So the first one, since it has x to the third, it is not a quadratic function. So I'm going to just go ahead and cross it out. The second one does have a variable raised to the second power, so this one would be a quadratic function. Let me go ahead and box it. The next one would not be a quadratic function because I see just the single variable t. This one would be a linear function because it has the single variable. And then in the last one, I see the x squared once again, so there's my second one. Now, remember, as I look at the graph, I'm looking for a U shape. So I know that this one is automatically not a quadratic function, and this one is not a quadratic function. This one is a quadratic function, and this one appears to be a quadratic function because they look like the letter U. Go ahead and pause the video and see if you can try this question. How can you recognize a quadratic function from its equation? All right, let's go ahead and look at the anatomy of quadratic functions. Graphs of quadratic functions are parabolas that open up This is what an open up parabola looks like, or down, that's what they look like. The vertex of the parabola is the maximum when it opens up, or sorry, opens down right there, or the minimum when the value when it opens up of the function right there. The min or max of the parabola does get a special name. It is located at the vertex. The axis of symmetry, or we can abbreviate it as AOS, is a vertical line that passes through the vertex. Since it is vertical, we will always write it as x equals, and of course it will equal the x value of your vertex. Determine the direction of the opening of a parabola by looking at the value of a when written in standard or vertex form. If the quadratic term's coefficient is positive, then the parabola opens up, and it would look like this. If it is negative, then the parabola opens down. So we're just going to look at that leading coefficient, and we're going to see today in standard form and vertex form, and we'll be able to identify without graphing technology if my graph is opening up or down, by if that leading coefficient A is positive or negative. The y-intercept is located where the parabola intersects the y-axis. Let's go ahead and take a look at this parabola right here, and let's identify its vertex, if it has a min or max, its axis of symmetry, its y-intercept, its direction of opening, and its domain and range. I can see that the vertex is this point right here. And so I'm just going to go ahead and use my x comma y to say that that is at -2, 4. And that's it. Depending on if that point, my vertex, is the highest point on my graph or the lowest point on my graph, determines if I have a min or a max. It is the highest, so I do have a maximum. And I have a maximum at the point -2, 4. It is at, the maximum is at my vertex. My axis of symmetry will be x equals -2, because my axis of symmetry is this line right here that is going vertically through my vertex. And I am using the x value. Notice I'm using the x value from my ordered pair to draw that line, because it is x equals. And it will always be x equals. All right, my y-intercept is this point right here. And my y-intercept is, of course, at the point 0, -4. Remember, in your ordered pair, x always comes first, then y. Be careful with the y-intercept, though. It is tricky. The direction of the opening for this one is down or downwards. You could either see it just down or downwards. The domain will always be all real numbers unless you have a word problem or a situation applied to your quadratic. But otherwise, it will always be all real numbers. And you can either write it out in words like I am right now, or you can use the symbol. The range is going to be y, and then you have to decide greater than or less than. It depends on if it's opening up or down. If you have a min or a max, these are all different ways that you can decide which inequality to use. Since I have a maximum, I am going to, that is the highest. So everything must be less than or equal to, there we go, my maximum value. I can't have anything higher than that. That's probably the quickest and easiest way to determine which inequality to use for your range. If it's downwards, then you need to use less than. If it's upwards, then you need to use greater than. The number that I'm going to pick is the y value from my maximum, the y value from my vertex. So it has to be less than or equal to 4. Let's go ahead and give a couple of these a try. So here is another one, and we're just going to go through and we're going to complete the process. Notice this time I don't have anything labeled. So my vertex is going to be this ordered pair right here, and that would be the ordered pair 3, comma, -1. I'm just using my x-axis first, 1, 2, 3, and then my y-axis second, -1, because remember the origin is my 0. All right, my axis, or sorry, not my axis of symmetry yet. I have, that is a minimum. And of course, remember it is a minimum. Where'd my at symbols go? At that vertex point. At that vertex point. All right, my axis of symmetry is going to go straight up and down right here through my vertex. This is my axis of symmetry, and it is going to be x equals the x value of my vertex or of my minimum, which are the same thing. My y-intercept is going to be this point right here, which if I just use my ordered pairs, it is at 0, 2. As I look at my graph, I can see that the direction of the opening is upwards. My domain will be all real numbers. I'm not even going to write it out this time. And my range will be y. And now remember, I'm going back. Minimum means this is the lowest that I can go. So it has to be greater than or equal to. And I'm going to pick the y value of my maximum, or sorry, my minimum, which is the y value of my vertex. Go ahead and pause the video and see if you can answer the try this. Sketch me a graph of a quadratic function with a domain of all real numbers and a range of all real numbers less than or equal to 0. All right, I'm going to go ahead and skip example 3 as we did that with our groups in class today. So that was something that I checked in class. You're welcome to pause the video and give this one a try. We did go ahead and do number 4 to get example number 4 together though, before we did example 3 on our own. And the reason for this is example number 4 is a little bit special. It has some restrictions on it. Notice this one does not have arrows at the end. Notice it starts here and it stops there. There are no arrows on it like you saw in example 2. The vertex will still be this point right here, which has already been labeled for us as 1, 10. As I can see, it is a maximum. It is a maximum. And of course, if you just want to write the word max for maximum, that is okay with me. It is at the point where my vertex is. My axis of symmetry, remember, will go vertically right here through the vertex. There's my axis of symmetry. And it's going to be x equals always and then the x value of your vertex or your maximum. My y-intercept is this point right here. And the direction of the opening is downward. These were all things that I felt confident that you guys could answer on your own. It was the domain and range that I really wanted to go over with you all. The domain for this one is not all real numbers because the arrows have been taken away. So remember, when the arrows are taken away and we do domain, we are doing a snapshot of where the x values are between. So we're going to use this inequality, less than x, less than. Since everything is closed on this graph, they're going to be less than or equal to x, less than or equal to. We're going to go ahead and put the left side first because remember when we do domain, we read from left. to right, to the left, to the right side of my graph. So the left side of my graph would be this number right here, and the right side of my graph would be this number right here. I'm using the x values of those 2 points. So these would be the 2 numbers that I would use. 0 goes here, and the 2.43 goes right here. For range, I'm going to use the same thing. I'm reading it from bottom to top. I'm going to go ahead and change my variable from x to y because I've changed from domain to range. Everything is closed once again, so I want to use less than or equal to y, less than or equal to y. Remember, when I read the range, I read from bottom to top, the floor to the ceiling. So the bottom would be this one right here, which would be 0. I'm going to go ahead and put it first. And the top would be this one right here, which would be 10. We also went ahead and did example number 5 with our groups today. So I'm going to go ahead and let you pause the video and go ahead and try to answer that one as well. All right, let's go ahead and talk about finding our zeros and our x-intercepts. The x-intercepts of a quadratic function are the coordinates of the points where the graph intersects the x-axis. The zeros of a quadratic function are the x values that return a y value of 0. In other words, the zeros are the x values of the x-intercepts. We can almost use them interchangeably. X-intercepts, zeros, they mean the same thing. But when we talk about the zeros of the quadratic function, we're not talking about an ordered pair. We're just talking about the x value of the x-intercept. That's the only difference between them. Let's go ahead and take a look at this graph right here, and we're going to go ahead and fill out this page. So we have our vertex right here, which we can see is at -2, -4. We can see because of the opening direction of it that this is a minimum. And yes, my minimum is at -2, -4. My axis of symmetry is going to go, remember, vertically through that line. There's my axis of symmetry. And it's going to be x equals every single time the x value of my vertex or my minimum. My y-intercept is going to be this number right here, this point right here, which is 0, 0. And my x-intercepts are going to be this one and this one. Uh-oh, let me bring that back. Yes, there are 2. There's one at -4, 0, and there is one at 0, 0. Yes, a point can be both the y-intercept and the x-intercept if it is the origin. Now, my zeros are going to be the x values of my x-intercepts. So I'm going to have 2 zeros, one at -4 and one at 0. And you could say x equals -4, x equals 0, or you could just say -4 and 0. The direction of the opening of this one is upwards or up. You could just say up. My domain, since my arrows are back, it is all real numbers, just like you guessed. And we're going to go ahead and do just y, and then we decide, do we have less than or do we have greater than, and then we use just one number for this one if there's no restriction to this one. Since I have a minimum, that is the very lowest number that my range could be. So everything must be bigger than it. So I'm going to go ahead and use greater than or equal to because everything is closed. Let me make that line a little bit better. Oops. I don't know why it keeps doing that. There we go. And I'm going to go back and pick my y value of my vertex or my minimum, -4. All right, let's go ahead and look at example 6. we're going to use our graphing technology to go ahead and graph this equation right here. In class, I showed you how to use the TI Inspire. I'm going to go ahead and do the best I can right here without any graphing technology. But I do encourage you that if you were not in class, that you have me show you how to use the calculator to graph this so that you can fill out this table. Now, what we saw was that our vertex was at 1, comma 4. So I'm going to go ahead and plot that point. 1, 1, 2, 3, 4. There's my vertex. We could see from our graphing calculator that we did have a maximum value, and our maximum value was, of course, at 1, 4. We saw this because the direction of our opening was downward. This is how we knew that we had a maximum. Our axis of symmetry will, remember, go right through this line right here, right through that point right here, and it would be at x equals 1. Remember, I'm getting that number from the x value of my vertex or my minimum. The y-intercept, we saw that the y-intercept was at 0, 3. 1, 2, 3. There we go. Due to the nature of our axis of symmetry, we also knew that there was a point right over here because the y-intercept is only 1 away from the axis of symmetry. There has to be a symmetrical point 1 away on the other side. That's the great thing about the axis of symmetry. We had 2 x-intercepts. Our x-intercepts were at -1, 0 and 3, 0. So -1, 0 and 1, 2, 3, 0. Just to show you one more time, 1, 2, 1, 2. That's the symmetry of your graph. Our zeros were at the x value of our x-intercept, so we would say -1 and 3. We could go ahead and draw the graph now. This is more than enough points to kind of get the shape of the graph. Let me go ahead and fix it with my program here. I can get it right on my points. Perfect. There we go. Perfect. That's what our graph looked like inside of our graphing calculator. And I showed in class how to get those exact points so that we weren't having to guess where to put that purple y-intercept and where to put those lighter blue x-intercepts and where to put that royal blue vertex. Remember, our domain, since we are just talking about a graph, is all real numbers, and our range is going to be y and the y value of your vertex, and then go back and look at this word right here. Maximum means this is the highest value that we have. Everything must be lower than it, so that is less than or equal to. All right, in our last example, we went ahead and used our graphing technology one last time to go ahead and graph these 3 graphs and to record their zeros and their x-intercepts. What I noticed from each one, when we graphed this one, it hit there and there and looked something like this. I'm just going to kind of draw a sketch right now, nothing too major, because remember, we're using our calculator. Our 0 was at -1. We only had 1 this time because it just touched the x-intercept there. So we only had the 1 x-intercept at -1, 0. For the next one, we had a vertex here at -2, 1, and then it went something like this is what it looked like. We had no 0, so there were none, and there were none. Yes, that can happen. Notice this is happening because this graph is not touching the x-axis. And then for our last one, once we put it in, it looked something, let me see, 1, 2, 3, 4. It looked something like this. Remember, it's just a sketch. My zeros were at 2 and 3, so my x-intercepts were 2, 0 and 3, 0.